All right, welcome back, everyone. Today, we're going to build a bridge. Not with steel and concrete, no, but with math and code. We're building a bridge from the world we all know, the world of classical data, into the seriously strange and powerful realm of quantum computing. So the big question we're tackling is this: how do we even get our data ready to make that journey across? Let's dive in. You see, the real challenge here is that classical and quantum systems speak completely different mathematical languages. This slide, you can think of it as our Rosetta Stone for this whole process. It's our blueprint, showing us the entire journey, step by step, from a simple classical vector all the way to seeing the quantum probability distribution. So here's how we're going to break it down. We'll cover this in 4 stages. First, we'll talk about this idea of the bridge itself. Then we'll get our hands dirty with data and vectors. After that, we'll actually build a quantum circuit from scratch. And finally, we'll get to see the really cool part, the probabilistic result.
Okay, let's dive right into section 1, the quantum bridge. First things first, before we can even think about sending our data on this quantum journey, we got to get our toolkit ready. And these are the tools of the trade. Think of this as our mission-critical software stack. We've got NumPy, the absolute powerhouse for all things vectors and matrices in Python. Then there's Qiskit, that's IBM's incredible toolkit that lets us build and simulate real quantum circuits. And finally, Matplotlib, which is going to let us actually see the results of our quantum experiment.
All right, on to section 2, data in vector form. And we're going to start on solid ground, right back in the classical world we all know and love, just to make sure we understand how data usually looks before we try to change a thing.
Look, in classical machine learning, it doesn't matter what you're working with. House prices, customer data, you name it. Your features almost always look like this, a simple one-dimensional array. In Python, using NumPy, this is our starting point. It's flat, it's simple, and we call it a row vector.
Okay, but here's our first, and I mean critical, translation step. Quantum computers, they don't work with row vectors. They need column vectors. And you might be asking, why? Well, it's because quantum gates, the operations we do on our data, are actually matrices. And for the math of matrix multiplication to work out correctly, our data has to be in this vertical column format. It's a non-negotiable rule in the quantum world. Okay, so let's pause for a quick pop quiz. Based on what we just talked about, if you have a classical vector with 4 features, how would you need to reshape it in NumPy to make it quantum ready? And the answer is .reshape for column 1. You're literally telling NumPy, hey, I need a structure with 4 rows and just 1 column. That is the exact format we need for a quantum gate to be able to do its thing.
This table, right here, really lays it all out. See, in the classical world, vectors are pretty flexible. They can have different shapes, any values you want. But the quantum world, it's a world of very strict rules. Quantum vectors must be column vectors, and their values aren't just random numbers, they represent probabilities. This rigidity, this structure, is exactly what gives quantum computation its power.
Okay, so our data is all prepped and ready. It's time to actually cross that bridge. In section 3, we're going to build a quantum circuit. This is literally the home for our quantum data.
And what's waiting for us on the other side? The qubit. It's the fundamental building block. And a qubit isn't just some abstract idea. Mathematically, it is a column vector. The 0 state, what we call 0, is the vector 1, 0. The 1 state, or 1, is the vector 0, 1. You see how that column vector stuff we just did now connects directly to the physics?
So how do we actually make one? Well, with this one simple line of code in Qiskit. When we type quantum circuit 1, we are creating a home for exactly 1 qubit. You can literally think of that little Q you see on the screen as a physical wire that's going to carry our quantum state vector. Okay, time for another checkpoint. When that circuit first powers on, like before we've done anything at all to it, what state is it in? Which one of those column vectors we just saw is flowing through that wire right at the beginning? Yep, it's always the 0 state. Quantum circuits have this predictable, known starting point. They are always initialized with that column vector 1, 0, which gives us a totally clean slate to start from.
And that, my friends, brings us to our final section. This is where the real quantum magic happens. We have our qubit, we know it's in the 0 state, so now we're going to apply a uniquely quantum operation and just see what happens.
We're going to do this with something called a Hadamard gate, and it's represented by that H box on our little circuit wire. And the absolute best way to think about it is like a quantum coin flip. It takes our boring definite 0 state and just, poof,
It puts it into a perfect superposition, an equal mix of both 0 and 1, all at the exact same time.
So what is superposition? At its core, it's this wild idea that a quantum system isn't just in one state or another, it exists in a kind of probabilistic cloud of all its possible states at once. But here's the catch, and this is the really important part. This strange state only exists until you try to look at it, or in our case, until you measure it.
So, what happens when we do look at it? Well, we run our simulation 1,000 times, and every single time we measure it, that superposition collapses. It's forced to make a choice. Am I a 0 or a 1? And since it started in a perfect 50-50 superposition, the choice it makes is completely random. Over 1,000 tries, we get about 500 zeros and 500 ones.
And this visual just captures the result perfectly. Instead of just staring at a list of numbers, we can plot them on a histogram. You see those two bars, almost exactly the same height? That is the visual fingerprint, the signature of a qubit that was in superposition. It's the direct result of that quantum coin flip we performed.
So let's just step back for a second. The crucial point is this. We started with a simple, totally predictable starting point, the 0 state. We applied one single quantum gate, and we ended up with a result that's purely based on probability. This ridiculously simple circuit reveals one of the most fundamental and powerful ideas in all of quantum mechanics.
So, I'm going to leave you with one final question to really tie this all together. What do you think our histogram would look like if we ran this exact same experiment 1,000 times, but we took out that one crucial step? We removed the Hadamard gate. Think about it. What does that tell you about where the quantumness in this whole process actually comes from?